I'm John. I work in the apps lab in Kratos with Sarah. My talk today is going to be about a kind of combinatorial approach, multi-sample analysis, or multiple analysis on one sample. My main motivation for this is we get loads of samples coming into the apps lab from customers. I'm sure a lot of you guys have a similar thing. And the common request is analyze my samples. Basically, they're kind of like, want turnaround as quickly as possible. Normally for me, it's a kind of panicky sales guy who's like wants an analysis report as back as soon as possible, but it could easily be a kind of optimistic PhD student who wants to get quick turnaround of their data. But we get all sorts of samples in. So as you can see from here, these are kind of like illustrative examples of the samples we get. Well, when you're handed it, or when you get it out of the envelope, it's obviously not a uniform sample. You can just look at it and it's got bright and dark bits, it's got topography. It's clearly not a homogeneous surface, but they just want analysis. So a kind of common thing to do is obviously then to just go, well, we'll analyze it in maybe 3 positions, 5 positions, and see what the difference is. So here's an example we had not that long ago, which was a sample of HIPG where copper nanoparticles have been deposited on it. And the question is, what is the copper concentration? So how much copper have I got deposited on my surface? And so if you scooch around and go in 3 different places, you get 3 different survey spectra, and you get different quantifications. Some places have sodium and chlorine present as well. But there's a big difference, as you can see, in the concentration of copper. One area you got 21%, other areas you got 10%. So when somebody says, how much copper have I got? It's a kind of difficult answer to give. And if you say, okay, well, the mean is 16.5%, that's not really representative of this total surface either. So what we have kind of dragged ourselves over to is basically this idea of mapping the whole surface now. So we had some discussion about imaging before. What I'm going to talk about imaging is parallel imaging, when people maintain the spatial distribution of the photoelectrons coming off the surface and use the 2D detector of the instrument to see the distribution of elements in one area. The problem with that for these types of experiments is the kind of logic of the workflow is kind of backward. You need to know what elements you're looking for before you decide to image them, because you need to sit at a single energy point. Whereas here, as Dave said before, we're basically doing scans at lots of different locations around on the surface. So we're setting up a whole array of analysis locations across the surface and macro mapping the whole distribution. Apologies to start with, because most of what I'm going to be discussing today is done on the Axis Nova, and I guess most of you guys don't have a Nova. It's my favorite instrument. We can go into that later, but if you see this is obviously not a Supra or Ultra sample bar. This is a Nova Platinum, and my talk kind of lends itself to that, because in the Nova you can basically put really big samples into it. Okay, so if you've got escape, the general workflow of setting up the experiment is, once you've got an image of your sample platen, so there's my big platen with loads of different samples on it, you can use this icon here, which is the analysis location icon for setting up the array. And then you can define lots of parameters on the size of this Cartesian coordinate system for setting up incremental analysis locations across the surface. Okay. The nice thing as well is, if you've already analyzed in one place, you can set the Z height so you don't have to do an auto Z at each location. It'll apply the Z height that you've previously applied to one of the locations on the surface, and then you can draw this. You can draw this grid out on the surface of the sample that you want to analyze. You can determine obviously the size of the spacing and or the step size or the number of locations. So once you've created this grid, and this is a kind of tip, is if you hold down the shift key then you get a kind of nice linear grid. If you don't, then it kind of goes off in all different directions. And then when you work up the data, everything can look kind of tilted. So that's one tip that I definitely recommend. Hold down that shift key, and then you'll get a nice square grid. When you've set up the grid, obviously, then it's just normal escape workflow of defining the experimental file, applying it, and then submitting that analysis as an array group. Okay, that means that all the data goes into this group folder. So when you do the workup, you can get this spatial analysis distribution plot, which you wouldn't be able to generate if you just had 10 different sample locations. Okay, so it has to be to be able to generate the data we'll be talking about, you have to kind of follow this workflow for setting up the specific type of analysis. Okay. So this is what we would have got in one location, where you can see the copper 2P has been fitted for one of the spectra on the left. We've got these 90 different locations on our sample. You could obviously do the auto peak ID if you wish to apply that. It would just peak ID'd, get a good fitted background, check that the start and endpoints all fit nicely, and then propagate that fitted background model throughout the whole spectral set in the modeling window. And then you can recreate in the spatial distribution a map of all the elemental composition of your surfaces. This kind of workflow sits really nicely in XPS as well, because you get to see relative distribution changes, and you're not just concentrating on the absolute concentration. Okay, so as we all know, the real strength of XPS is in a relative comparison of atomic concentrations, if we want to talk about quant. So here you can see this is the surface once again, and you can see a big distribution difference in the copper and all the different elements. You can see there's also correlative features here. Where it's hot with copper, also it's hot with oxygen. Where it's darker, you have a lot of perhaps adventitious carbon on the surface, or just you're seeing a lot more of the HOPG underneath. The main motivation is then, so obviously these people are interested in the copper nanoparticles, they're not interested in the HOPG. You could then go along to one of these locations, M7 here, and then you could do subsequent analysis of that location and identify the oxidation states. So instead of just sitting in one location in the middle, because it's geographically in the middle, so that's where people naturally tend to analyze, you could find where the area of concentration is highest, go there in this mapping routine, and then get the information on the copper. So here we got the copper 2P peak. Because of the lack of the copper 2 shake-up feature, we could identify it as what is it, Cu2O, and then that was the answer that the customers were looking for this project. Obviously, some of these experiments can take quite a long time to run through. So there is a certain degree of experimental design optimization that you need to kind of go through, where the importance is getting as much information as quickly as possible. If you've got 90 locations or 200 locations, if you run a survey scan for 2 minutes at each place, you can rapidly start to stack up on the time. So some of these experiments are overnight jobs rather than just kind of sitting in the afternoon. But they can be optimized by trimming the size of the survey scan, or using the snapshot mode of the spectrometer as well, where instead of doing minute scans, you're analyzing in a location for maybe a second or two, especially on the kind of bright lines or those elements that have got a high concentration already. So there is a certain amount of optimization that you can go through as the analyst during the process. So moving on from just an illustration of just a standard sample coming in, this was an application which we looked at with the University of Manchester with Alex Theodosio, and his sample was basically an ion irradiated, so 50 kV cesium ions. These were performed in Shanghai ion beam facility. And so what we were doing was we're damaging nuclear grade graphite with cesium ions, and then looking at the distribution and what's happened to the carbon 1s, what's happened to the graphite after the ion bombardment. So he gave me this sample, and as ever, he just said, "Oh, can you analyze it and get me some data? I'm desperate." And so you could look anywhere, and whatever data I sent, he was never happy with it. So I just said, well, you know, your sample has got, we're going to have to analyze the whole sample. So we basically mapped out the whole array of this 1 centimeter size piece of nuclear graphite. And you could basically see that the distribution of the cesium here, so it ranged from about 15%, I think, down to basically 0. So down in the corner, no cesium ions hit down there. So we looked in different areas, and you can see that obviously the distribution of the ion bombardment process that he'd performed wasn't uniform across the surface. So where exactly are you looking? What is your sample then? It becomes kind of like a complicated question, really. So we analyzed basically in all 90 locations to get that concentration distribution. Here are 4 locations in particular, because I don't want to show you like all the data kind of like fitted, but you can see that there's you already start to just mount up a lot of information when you propagate through a fitted model of a survey scan. You start to get a lot of data, and you end up with tables like this, which are really difficult to understand, because it's difficult to kind of like see the relationships are there. But basically, in position D, I'm not going to go into the science of this particular project too much, but in cesium D, it's almost all carbon. Obviously, it's the graphite sample, and there's very little oxygen. Where we see lots of cesium, we also see lots of oxygen. So there's some sort of reactive process going in during the implantation process as well. The motivation was also to see then the distribution of and the change in the carbon chemistry. So Alex's real interest was seeing the destruction of the graphite structure, seeing the destruction of the sp2 bonding, and seeing if this caused a buildup in say Wigner energy or a change in the lattice arrangement of this material. And obviously that's because these rods, graphite's used in nuclear reactors to kind of like quench the process. So we looked in these 4 positions again, and you can see in position D, this just looks like HOPG. This is data acquired with a silver source. So this is a silver L-alpha, and that's aluminium A-alpha. Just so you clear, 1486, 298, 2984. So on the right, we're looking deeper. On the left, we're looking shallower, essentially. And you can see at D, this is where no cesium has effectively hit the sample. And then we've got 3 different levels of basically cesium bombardment. I think it's 5, 10, and 15% of cesium you can see in the surface. Again, you can see different levels of destruction. So this sp2 peak is kind of decreased, and you start to see this larger component coming up. And as you get more cesium, this gets destroyed more. And effectively, by the time you've had a large amount of bombardment, then the sp2 peak is basically gone. And we can see the similar relationship happening using the silver as well. We're looking deeper here, and that's why there's less reduction there's less destruction of the sp2 component. We're in that kind of sweet spot where you can use both X-ray sources to kind of probe that. The really nice thing about this was it was difficult to understand how to peak fit it, and carbon 1s, there's not a lot of information in it. So the real benefit we had was when you're trying to get a kind of fit of what the different components are and what it all means, is we had spectra from 90 different locations. So then you can go back to all of that spectra and try and find a fitted model that is a one-size-fits-all. So it has to be able to fit all the different spectra to be able to and propagate through to be able to satisfy what we're seeing. So that's a kind of one-size-fits-all solution. If we hadn't done this, you'd just analysed in one location and just drawn one conclusion. That's the kind of overall message for this. But the interesting thing was basically correlating the change in the different carbon 1s peak shapes and seeing how that was affected by the bombardment of the cesium. That was one way of that was one motivation for the project. Sorry, I'll just have a glass of water. I've also had a bit of a cough as well, but it wasn't COVID, I don't think. So the next thing I'm going to talk about was done a while back with Nottingham University, and this is Biomaterials Discovery. And so it's a similar sort of vein, whereas but in this case, it's not one sample and just looking at how inhomogeneous the distribution is. It was an array of different polymers basically printed on glass slides, and we got an array of, I think, 144 different polymers printed, all different monomer groups. So the motivation for this is to basically have a high throughput screening of different polymers and analyzing it using different techniques. So they got SIMS and they got Raman and different probes, and looking at and correlating together the different bits of information you get from the techniques. Okay, so this is a glass slide. This is an image of this glass slide with the different polymers on top of it, and essentially that's, instead of it being one sample, it's like looking at 144 samples. Okay, so they put all the polymers down and then apply a serum, like a protein serum, across the polymer set, wash the serum off, and then see if there's any functionality change in the polymer that was there. So is that polymer interacting with that protein serum? Is there any binding? Is there any change in the process, in the surface of that material? So once again, the workflow is the same. So you create this grid, propagate it across this whole array. This is a beautiful stitched image, optical stitched image of the array, where you can see all these little dots of where the polymer dots are. These are printed on with a basically like a inkjet printer. And so this is a kind of zoomed in version of these kind of different polymer blocks, and each one is it's got a different monomer chemistry. So you can see here that you've got, if you get spectra from each place, you've got some have fluorine in them, some have nitrogen in there. Everything's got carbon and oxygen, but you've got different chemistries going on it at each different location. The nightmare for this was that actually all those polymer dots are not quite lined up. They're all plotted in slightly different places. So for each location, I had to go along and optimize it optically so I was looking in the right place, and that took hours. But I did. But in a nice world, you know, it would all be, and we could just draw the grid on top of it. But that's just one of the pitfalls of these kind of experiments as well. So it's 144 materials really that you're analyzing in one method, and so you get these distribution plots. This is prior to the application of the protein. You get these elemental distribution plots, so you can see carbon, oxygen, nitrogen, fluorine. These correlated with the expected chemistries of the material. The protein solution was then applied and then washed off, and you could see this plot now is a subtraction of the difference in nitrogen concentration before and after. Okay, so we go to each different location, and green basically means nothing's happened. Okay, but there are certain places like the blue, because it's a color scale, the blue where it's gone down, red where it's gone up, something like this. Okay, so the nitrogen is a marker for the protein really. So in this one, we can see the nitrogen concentration has increased dramatically. Okay, so it's gone up. In that case, this was the spectrum beforehand, the blue, and after we get the nitrogen 1sp increasing a lot, and that corresponded to the right binding energy for the protein serum as well. In this case here, it went down. So you had before, no, it went up. So you had before, it was lower, and then as we increased with after the protein addition, the concentration went up as well. There's also changes in the carbon chemistry as well, according to like the uptake and or not uptake of the nitrogen protein. So that was a nice way of looking at like a whole database of different polymers. at once, and being able to quickly see which ones have picked up and interacted with the protein and which ones hadn't. The nice thing is you can then also go back to each location and do more analysis if you want to as well. High throughput, high screening. You can see the data's a little bit noisy on some of these. You're looking at 144 samples, so you're always like, you know, time becomes a big thing when you kind of, you know, looking at the setting up the initial acquisition. So when you press go, you know, you don't want to have, you know what I mean, over scanning or under scanning for a particular element. So that kind of experimental optimization is a bit of a thing that you can quickly see just in the simple color scale, you know, which ones have been important and which one hasn't. And if you look really closely, all of these circles are not quite aligned. That's because it maintains the actual geometry of those samples. You can also export out and escape the table of concentrations as well. But these become huge, and it's only then that you realize how impossible it is to see anything, because you've just got so much data. And especially if you've done fitted models for each of these spectra as well, it becomes a huge kind of matrix of information, which you can see a lot clearer just in a simple picture. Also, I think, you know, when we've done kind of online demos and stuff, I think like managers like to see pictures, because it kind of just says stuff, rather than, they don't like to see spectra, they like to see a picture. It kind of like means a lot more. So this was another bit of it where we also looked at the change in the fluorine concentration, which wasn't related to the protein serum, but we didn't expect really to see any change. We saw in this place the fluorine peak had actually increased significantly before and after by applying the protein, which is kind of nonsensical really, because protein didn't have fluorine, but the polymer previously did, but we were getting very little signal. But the application of the protein and the wash afterwards actually ended up maybe bringing some of the fluorinated like structure to the surface, and we could see a lot more of it. So it wasn't just looking for the addition of the protein, but also the effect of the protein on the polymer as well. The last application, how am I doing for time? Am I rattling through this, or am I like spinning it out? I can't work out. Yeah. Okay. The last bit I'm going to talk about is the novel alloy systems. So this is to do with a material called nitinol or nitinol, and it's basically used in shape memory effect alloys. So this has got kind of applications in kind of like medical devices, and also kind of like materials where you can deform something, and then under temperature or stress or a magnetic field, then it will go back to its original shape. Really interesting materials. And they've got lots of kind of like applications for like really small devices as well, just for as kind of like switch or sensor materials. So this was a project with the University of Maryland, and we weren't looking at an actual device or anything. They were looking at entire material systems. So they were looking at screening large databases for basically kind of like material design optimization, etc. So you've got a material library here. So this was basically a film, sorry, not a silicon film, what was it? It was sapphire, a sapphire plate deposited with 3 different metals in a depth chamber. And then that would go through different characterization techniques like XRD, force probe stuff, resistivity as well, and basically looking at kind of like correlative effects and linking chemistry, linking like material characteristics to performance, etc. So that's XPS kind of fitted in with that, because it's quantitative and it gives kind of surface information as well, as we know. So that's where it sat in the kind of like material matrix for this project. As I said, nitinol is nickel. It's got nickel, titanium, cobalt in it. It's used in a few different applications. Of particular interest is the addition of cobalt. It changes the material properties significantly, and also it's kind of like reversibility process. And in this project, the cobalt hadn't been looked at significantly, but it wasn't just the only element in the whole project. There was other kind of like top row transition metals that were being looked at as well for this transformation. So once again, we had this sapphire plate with all the distributions of different concentrations across the plate deposited. So you had in the deposition chamber, you had nickel, titanium, and cobalt in different orientations, and the assumption was obviously that gives a kind of even distribution in different places, and these weren't actually to be looked at for looking at titanium and cobalt kind of distribution in particular, but mainly for like doing lots of different experiments on the same material concentrations. They had boxes of these and crates of these different ones where they would have deposited for different amounts of time. They didn't believe there was necessarily a distribution across the wafer. Okay, obviously there's a lot of different sample locations. So we did 60-second fast acquisitions here. So that's a whole stack of spectra. Once again, to kind of look at. So you apply your backgrounds and then propagate that through the data fitting in the modeling window and escape, and then you can pump out the distribution maps. And here I haven't used the circles because these aren't individual locations really. This is a whole distribution across the wafer. The nice thing is if you get your model a bit wrong, you basically just get the same plot anyway. So even if you get kind of like spikes, or if you use Shirley or two-guard, it all ends up giving you the same picture, really. These are not absolute concentrations, as you can see. I haven't labeled anything up. I haven't got any scale bars on there. This is relative distributions across the surface. And straight away you can start to see things. So obviously, as you would have guessed, the kind of geometry of your depth chamber, there'll be more cobalt, there'll be more nickel near where the nickel source is, etc. That's kind of obvious. But you get there's straight away a correlation between titanium and oxygen. It's really reactive, so it obviously gets some of the oxygen out when it's being deposited. And also this carbon effect. You know, you kind of always think, you know, additive of carbon is the same amount across the surface. Well, there's quite a distribution difference, about 20% across the surface as well. So maybe that gives you information about the kind of how reactive the surface is to picking up that kind of material, or whether there's kind of contamination coming in during the deposition process as well. The nice thing is you can then get. So those were just survey scans, 60 seconds over about 200 locations. So you can quickly work out the kind of time periods for these. So you've got a few hours. You can then go and do high res spectra for the different elements. So these were relatively quick spectra. I'm thinking around about a minute or 2 minutes. These are low concentration. Nickel's quite a low concentration element for this material, but like. These experiments are hours, not days. That's what I'm trying to get across. So you could basically get nickel, the nickel 2p region. You could put some sort of, I'm not going to argue about the validity of the peak fitting here, but there's basically a metallic component. There's a 2+ component, and you can kind of propagate that through the whole spectral set again. Okay, constrain the fit and the position, and you can get a distribution map then obviously of oxidation states, not just elemental distribution. And you can see that it doesn't really correlate with the actual elemental distribution. So you can see this hot part up here from nickel there, and it goes cold. There's a change in the actual distribution of nickel 2+ and nickel metal in a different area that doesn't relate to the elemental distribution. And you can, just to prove that, you can kind of go to like different areas and see the peaks that correspond to the kind of 2+ and the metal peak. What all that means, how that means for the actual material is pretty complicated, really, and it posed a lot of questions to the people we were working with, trying to understand why that would be the case, etc. The nice thing is you can still just go to any of these locations and then kind of dig in where you've seen something interesting. So here we did depth profiling. The main interest was because these guys were like, okay, well, we're doing materials analysis, but not particularly, you're obsessed with the surface. I want to see what's going on in the bulk really. Is the bulk representative of what you're seeing on the surface? Because I was always saying there's loads of carbon there, and they're like, there's no carbon in my material. But that's the kind of, conversation between people from different groups, I guess. So we depth profiled the materials in 2 different locations in 76 and 218. And as you'd expect, you'd see the carbon decreasing significantly in the first 15 seconds as you kind of taking away a bit of rubbish. What was quite interesting here was you take away some of the carbon, and then titanium immediately goes up, correlating with oxygen, and then goes back down. So there was a certain, in this area, there was an enrichment of titanium right at the surface, and then it goes back down to a kind of steady state. And we don't see that in this area as well. So you can see there's definitely enrichment processes. So that kind of had to be explained to Naylor as when we're talking about bulk surface, those kind of situations. It's great when you do these kind of experiments because you end up with so much data as well. You can really kind of like dig into it. We try to do kind of intelligent data system kind of thing as well, where you kind of like could just feed the data straight into a kind of program, which she had with XRD, and it will just spit out what the results are. Problem is XPS data is really horrible, and like there's loads of weird features and backgrounds and stuff like that to deal with. So it wasn't simple. And we ended up putting in a lot of kind of like bias into the kind of fitting. But here's something which, if you just run this individually, you might not spot. So we've got the spectra from, these are 30-second spectra. We've got the carbon-1s spectra from all over. And you can see every now and again, you can see there's this little bump down here. Okay, it kind of comes and goes as you go across. These are lined up like that. Okay, so that's the carbon-1s distribution you can see. That's the elemental distribution. But if we just take the normal, boring carbon-1s peak that we think is just adventitious carbon and propagate that model through, you start to see. I labeled this up as carbide because it's going to have to be carbide that low down. And then you get a distribution map where you're getting some sort of carbide formation down this bottom corner. Okay. So if you then go to one of those locations and depth profile it, okay. So this is the titanium 2P is the green as we go through. This is the titanium rich part of the sapphire disc. As you start to depth profile, you see the titanium go up and go across. So it's relatively high, in the high 20s. Oxygen comes down as you decrease the titanium. And the carbon kind of goes steady state around about 5% or so as you etch in. But you start to see this carbide peak kind of stays in the position. I know what you're thinking. You're thinking, oh, I'm making that by hitting it with ions. But if you do the same experiment somewhere else, you don't get that peak. So don't start saying that. So we can fit that out as well for the depth profile, and you get to see there's basically this kind of like steady state carbide peak going into the bulk of around about 2% as well. So that was interesting for them because then they could look at the XRD data for the map of the same thing, and they could see carbide in this region and not in the other. So it fitted with the kind of peak identification that they'd seen. So that was one of the nice things, when it all kind of like knits together and works. It's kind of neat. But obviously we've been told that there's carbide there by working up this big data set. So what carbide was it? Is it related to titanium, I wonder? So we looked at the titanium 2P peak, and you can see that it kind of changes a little bit, this kind of shouldery thing. So you've got the metallic and you've got the TiO2, the 4+ peak, and which is the dominant peak there. And it's kind of got an awkward shape, and it's a bit difficult to kind of like peak fit titanium. But we had a go. And so you've got the different you've got the reduced oxidation states between the 4+ and the metallic state, which think of an alloy, basically TiNi. You've only got very small amounts of cobalt, and in between you can kind of fill out the components with other things. We know this goes down, we know this gets bigger, and so we kind of called it TIC first of all, and there's a kind of 3+. This is the carbide distribution, just so as you remember, that's the carbide here. So you can see the carbide's rich down there. If we put this component in and put it through the whole data set, we get this. So you can see it correlates directly with the carbide that we've identified from the carbon SP. So we're pretty sure, in the literature, if you look up titanium carbide, you can put it wherever you want, really, depending upon what kind of what you want to fit your story. But we constrained it there, and it fits with the carbide distribution for the Carbon-S. And you can see this top to bottom distribution of metallic with the alloy and the two different oxidation states as you go up, which is in the opposite direction to the actual elemental distribution of titanium. So that's it. Basically, you can analyze a lot of in a lot of different areas on the same sample, or you can analyze a lot of samples. But I think you get a lot more information by acquiring more data on the same sample in different locations, and then doing a kind of, you know, a one size fit all kind of experiment. That was particularly useful for the cesium stuff and for the nitinol materials. You just get to see relationships that you wouldn't pull out if you're just analyzing places. Obviously, the real benefit comes with having a high performance spectrometer. So, like, you're blessed with Kratos spectrometers, so you can really dig into and get your sample analysis and your throughput up significantly. Last of all, I just want to thank all the guys who've worked with Nottingham, Maryland. Ed, who used to be a software guy at Kratos, he was great in kind of like working. This problem originally came, we did a demo for like Bochum University years ago, and they bought a Nova, and they wanted to do stuff like this, but they only had vision. And to do it in vision is possible, but it's a real headache. Well, you don't get any of the pictures out, but even setting up the analysis positions was really difficult. So when Escape was going to be moved onto the Nova, we wanted to make sure that you could do all what they wanted, these kind of analyses. So Ed was really good at working with that and getting it just right in the software so we could do it. And work with Manchester Uni as well, Henry Voice Institute. So anyway, thank you.